everybody. I'm pleased to introduce Hailey Jee, our final speaker for today's workshop. And she will be telling us about characterizing quantum correlations with fixed dimensions. Hailey?
Thank you. Yeah, thank you. My name is Hailey. Thank you for having me here today. In this talk, I would like to talk about our recent paper on arXiv about characterizing quantum correlations of fixed dimension. Our main result is that we provide a classical algorithm to characterize fixed dimensional quantum correlation. So this work is more about classical algorithm for quantum problem rather than quantum algorithm for certain problem. So why is characterizing correlation important in general? It's important because it is a way to understand the quantitative advantage of quantum resources. So in that sense, it's interesting from both fundamental and practical point of view. So for example, Bell inequalities, which is the most prominent example where this characterization of quantum correlation can be applied. They provide fundamental locality constraints from the physical point of view, but at the same time, they also play an important role in device-independent quantum information processing field. And particularly why the reason fixed dimensional quantum correlation is interesting is because they can be used to quantify quantum advantage in terms of dimension. So for example, they can be used as a dimension witness in this device-independent quantum information processing. And this is why we would like to study this topic. So there are many different mathematical tools to characterize correlations in general, but we would like to use this non-local game concept today. I guess you're already quite familiar with this concept because there were a few talks today about this, but still I will explain it quickly again to some people who might have missed it. So in this non-local game scenario, Alice and Bob play a game against the referee. If the game starts, the referee chooses the questions Q1 and Q2 according to this probability distribution pi, and then send them to Alice and Bob. Then Alice and Bob have to provide answers A1 and A2 to the referee again. Then referee checks whether the answers are correct or wrong according to this rule function V. So this rule function V has the element 1 if answers A1 and A2 are correct for the given questions Q1 and Q2, otherwise it has 0. So the referee checks this and then tells Alice and Bob whether they have won the game or not. Alice and Bob can agree on the strategy beforehand, but after the game starts, they can't communicate to each other. In general, Alice and Bob's strategy can be described by a correlation between two parties, and mathematically can be represented by this joint conditional probability distribution P. And there are many different sets of correlations, such as classical correlation and quantum correlations. And depending on what kind of resources Alice and Bob have access to, they can perform better or less in the game. So to quantify the differences in advantage of different kinds of correlation sets, we will use the quantity success probability, which is the probability that Alice and Bob will win the game. So for a given game described by this rule function V and the question probability distribution pi, if Alice and Bob agree on a strategy P, then you can calculate the success probability by this equation. And depending on the correlation set Alice and Bob can exploit, you can define different kind of optimal success probabilities. So for example, if they are only allowed to use classical resources, you can define this omega C, classical optimal success probability, which is also called as classical value in the computer science field, I believe. They can have this form. So in this case, the classical correlation P has this form because Alice and Bob cannot communicate to each other. So their answers will only depend on their questions only. So this will take this form. And if you maximize over all kind of this probability distributions, then you can get the classical optimal success probability. And if they are allowed to use quantum resources, then you can define this omega Q quantum optimal success probability, which is also called a quantum value. And then in this case, quantum correlation P takes this form. So now Alice and Bob can share entangled state rho and perform a measurement E and D on their shared state and use the outcome probability of this measurement to provide an answer. And if you maximize over all possible states and measurement operators and even the Hilbert space of rho, then you can get this quantum optimal success probability. But sometimes you are interested in the case when this shared state has fixed dimension. So for example, you might want to know how well you will do only using qubits. So in that case, you can define another value, quantum value of fixed dimension T, which is omega qt here. And this has the same form as omega q, except that it doesn't maximize over all Hilbert space. So this is the quantity we are interested in this game. And calculating these values are important to understand the quantitative advantage of each resource. For example, the difference between classical and quantum resources can be captured by Bell inequalities. So if Alice and Bob are only allowed to use classical resources, then they must satisfy this inequality. And in the case of CHSH game, the rule function V takes this form, and the probability distribution pi takes the uniform distribution over all Q1 and Q2. And in this special case, the values of omega C and omega Q are known. And then this part of inequality represent the CHSH inequality. And the fact that omega Q is strictly bigger than omega C indicates that you can violate this CHSH inequality by using quantum resources. So these values are important because they give us this kind of quantitative advantage of each resource. But in general, for general non-local games, calculating these values are known to be very, very difficult. So instead, people have been developing approximation algorithm for these values. So for the general quantum case, when you need to maximize over all Hilbert space, the MPA hierarchy provides an effective classical algorithm to approximate this omega q. And it has been widely used in the quantum information science field already. But for the fixed dimensional case, there have been a few results on this, and some of them provide a practical algorithm to approximate this omega qt. But in most cases, analytical asymptotic convergence speed, which is the convergence speed of approximation algorithm for a given constant error epsilon, is either not quantified or at best exponential in the size of the game, so which is the size of answers and questions. So our goal is to develop a new approximation algorithm for characterizing quantum correlations of fixed dimension with good analytical convergence speed to approximate this value omega qt. In the rest of the talk, I will try to explain how we derived this new approximation algorithm and how we prove the convergence speed of this approximation algorithm. To derive the algorithm, our approach was to connect the problem characterizing quantum correlation of fixed dimension to the quantum separability problem, which is the special kind of optimization problem which I will explain later, and exploit the non-semi-definite programming relaxations for this separability problem to derive a new algorithm. And then we will exploit quantum definity theorem to show the analytical convergence speed of the algorithm. So from now on, we will focus on these 2 points. So let's go back to this non-local game. We want to talk about these free games because in our work, we only consider this special class of non-local games. So free games are the games in which the choice of the questions Q1 and Q2 is not correlated. So when the probability distribution pi takes this form, this product probability distribution form. The reason we focus on this case is because it improves the convergence speed significantly. And also, most non-local games considered in quantum information science field are actually free games. So for example, CHSH game, the pi was just uniform distribution, which satisfied this. So it doesn't restrict ourselves a lot physically. We have that's why we focus on these free games, but we have a result for general games as well, but it doesn't improve the previously known convergence speed a lot. So in this talk, we will only talk about the free game result. So this is the quantity we are interested in, that we want to approximate. And now I replaced this pi q1 q2 with this just product form, because now we are focusing on free games. And our aim is to connect this to the quantum separability problem now. The quantum separability problems originally refers to the problem to distinguish whether a given state is separable or not, but it also refers to an optimization problem in which the optimization is taken over all separable states. And in this talk, this term refers to the latter, the optimization problems over separable states. And our aim is to show that this omega qt, this optimization problem, can be converted to an instance of the quantum separability problem. And in the next few slides, I would like to show that to you. So now we have this separate pi q1 and pi q2. So they can be observed in E and D measurement operators here. So we did that. So now we don't have pi q1, q2 here, and they're in this E and D. And now the operators E and D are redefined as this. And now we want to use everything, we want to make everything quantum. So there are now these classical indices in this free root function V and E and D, but we made everything classical quantum system. So now this root function V is a diagonal operator V whose diagonal element is this V. And this measurement operator E and D also have this classical register part, which indicate this indices A1, Q1, and A2, Q2. And now we have this additional linear constraint on this optimization problem to make sure that these operators E and D are the measurement operators E and D here. And there are these t squared terms because we divided E and D by t to make this state, this part normalized, because it's convenient later. So this is the intermediate step. And now we want to use the swap trick. This is the definition of swap trick. If there are two operators A and B in the same space, the trace of multiplication of those two operators can be written as trace of tensor product of those two operators times the swap operator F. And the swap operator is the operator permitting the system T and T hat. By simple algebra, you can show this. And we would like to apply this to the objective function of this omega qt. So between this rho and E tensor D. And if you do that, you can derive this formula. And so originally rho and ED were multiplied in this trace, but now they're in this tensor product form. And we have this additional term swap operator here because of this swap trick. And also we want to use the fact that this the swap operator is actually a partial transpose of unnormalized maximally entangled state. And if you take that into account as well, then you can arrive to this final form of this omega qt, final expression for omega qt. And now there is this phi instead of f. Here, phi is non-normalized maximally entangled state. And there are this same additional linear constraint to make sure this E and D are the measurement operators E and D in the in the original expression. And if you look at this closely, then you can notice that now all the optimization variables are in this part, and they're in a product state form with respect to this tripartition. And because product states are the extreme point of separable states, so maximization over product state gives the same value as maximization over separable states. So you can think this maximization as a maximization over all separable states with respect to this tripartition. So in that sense, now this omega qt, this expression for omega qt can be seen as an instance of the tripartite quantum separability problem with this additional linear constraints. So we achieve our goal. But I would like to emphasize that this form of omega qt has this additional linear constraints related to these measurement operators E and D, because they play an important role in later. So please try to remember that there exists this additional linear constraint in the quantum separability problem form of omega qt. And now we would like to use the known relaxations for this separability problem to derive a new approximation algorithm for omega qt. So we would like to use the concept extendable states because of two reasons. First, there are good approximations for separable states. And second, they have an efficient characterization via semi-definite programming. So you can efficiently check whether a given state is an extendable state or not via semi-definite programming, which is very good. And this is the definition for extendable states, but it can be described by a simple picture. So if rho AB is you call this rho AB is n-extendable if you can find an extended state rho AB tensor n, which has all the marginal state between any pair of AB as the original state rho AB, and also if it's invariant under any permutation on B systems, and if you can find such extended state, then this rho AB is n-extendable. And this is related to the monogamy of entanglement. Entangled state cannot be shared, but if the fact that you can find this kind of extended state means that this rho AB can be shared by many different parties. So which means rho AB should not be very entangled. That's why there are good approximation for separable states. And these extendable states have a convenient property that rho AB is n-extendable for all n, if and only if rho AB is separable. So if rho AB can be shared by infinite copies of B, shared for infinite copies of B, then this rho AB is actually separable. So if you draw a diagram, it will be like this. So it can be easily seen that higher n extendable states are always included in lower n extendable states, because you can always trace out some B systems to find the extended state for the lower n case. So as you increases n, the set of n extendable states becomes smaller and smaller, and when n reaches the infinity, it coincides with the set of separable states. So they form a hierarchy of good approximation set for the separable state. So we would like to use this. So this one was the objective function of omega qt in the quantum separability problem form. And these were the product state. Also, you can think this as separable states. And what we want to do is to replace this part with n extendable states. And now the maximization is over all n extendable states. And we define this as nth level semi-definite programming relaxations. And if you do that, then because the set of n extendable states is larger than the set of separable states, this SDPN provides an upper bound on this actual solution omega qt. because now you maximize over a larger set. And if you increase n, then it gives you tighter bound. And if it reaches the infinity, it becomes equal to omega q2. So this provides a converging hierarchy of SDP relaxations for the upper bound of omega qt. And this is the full description of this SDP relaxation. So it's quite long, but I will explain to you it line by line. So this is the objective function we derived earlier. So rho here is an extendable state. And the first line makes sure that this rho is a normalized quantum state, so it's density operator. And this second and third line are from the extendability constraint of this rho. And here now we are using tripartite extendable states. Earlier we only talked about bipartite extendable states, but it can be generalized. The concept can be generalized to the multipartite case straightforwardly, and all the properties are same in the multipartite case. And here we are using tripartite extendable states, and so that we have these two permutation invariant constraints from this extendability constraint of rho. And this last two constraints, they are from the original additional linear constraint existed in the quantum separability problem form of omega qt, the one related to the operator E and D. So if you write them in terms of rho, then they become like this. So they are the original additional linear constraint from the non-local game scenario. And to get the tighter bound, you can additionally add PPT constraint to make sure this rho is close to separable states, as well as MPA constraint. So this is the approximation algorithm for omega qt, which characterizes the quantum correlation of fixed dimension. And now the remaining task is to show that this has a good analytical convergence speed. And to do that, we would like to exploit quantum definity theorem. So standard quantum definity theorem provides a quantitative bound on how close any extendable state to the set of separable states in trace distance as a function of n and dimensions. So in a simple picture, it means that this standard quantum definite theorem provides an upper bound on this distance between an n extendable state and the set of separable states. So it can give us information on how accurate our SDP relaxations are. But unfortunately, our SDP relaxation have a special structure that this rho AB is not only just extendable states, but they're extendable states satisfying this additional linear constraints. And the existence of this additional linear constraint makes it impossible for us to use the standard quantum definite theorem. What we want to know is the distance, upper bound on distance between an n extendable state satisfying linear constraint to the set of separable states satisfying this linear constraint. So we couldn't use the standard quantum definite theorem, and we had to use an appropriate version of quantum definite theorem. And also another fact is that we are using multipartite case, a tripartite case. So in the same paper, we proved multipartite quantum definite theorem with linear constraints using entropy inequality proof technique. And this is the statement, but the important part is just this part. What it says is that when this rho ABC is n-extendable, so that you can find this kind of extended state, rho AB and Cn, and if this state satisfies this additional linear constraint, then you can always find a separable state which also satisfies this same linear constraint and is close to rho ABC with upper bound this in terms of n and dimensions. So this gives you upper bound on this distance. So this can be converted to the upper bound on accuracy of our SDP relaxations. So this SDPN is close to this omega qt with upper bound this, where A is the number of possible answers and T is the dimension of shared quantum state. And this implies that with these SDP relaxations, we can estimate omega qt within a constant additive error epsilon in time this. And for fixed T, this dependence is quasi-polynomial in A, the number of possible answers, and polynomial in Q, the number of possible questions. And this improves the previous work for which the worst time guarantee was at best exponential in both A and Q. And that was our main contribution. And we believe that this dependence in terms of A and Q is optimal because when you take the classical limit, when T goes to 1, this complexity result matches the best algorithm for calculating classical values of two-player free non-local games. So we believe that this will be optimal in terms of A and Q. But for this T dependence, whether this is optimal or not is still open questions. There might be, we don't know yet, but there might be another algorithm which can have better dependence on T. So this is how we prove our convergence speed. So in conclusion, we give a converging hierarchy of SDP relaxations for the set of quantum correlations with fixed dimension. And we provide analytical bounds on the convergence speed by means of multipartite quantum definite theorem with linear constraints. So these are my supervisor and collaborators. I would like to thank them for all their help on this project, and thank you for listening. Yeah, I'm happy to have any questions.
Thanks a lot, Hailey, for this, again, very clear talk on some interesting connections between various topics in QI and non-local games. So let's see. So far, there are no questions in the Slack. So let's wait for people to start asking questions. In the meantime, maybe I can ask a question on on this kind of comparison with the previous work by Navascués with the they also had SDP relaxations in their they're also wondering, maybe you've already mentioned it. I was wondering if you can comment on the scaling with the, I guess, dimension on D. Dimension on D. Okay, sorry. Yes. So the previous work, sorry, it's a long way to go. Yeah, this Navascués work. So there, some of them is quite actually they use the similar idea as us, the connection between quantum separability problem, but they use the special case. So dichotomic measurement. So for the dichotomic measurement, so when the answers are only 2, and in that case they didn't really analyze the convergence speed, but in the appendix or appendix, I think they just mentioned that they scale in exponential in terms of this A1 Q1. But it was one thing, and the other two they used a similar idea as MPA hierarchy, this moment matrix thing. And also I think they didn't. So I think they analyzed their convergence, but it was also exponential in A and Q. So, but I think for this works related to this MPA moment matrix thing, I think they tried to, their aim was a bit different from us. So they tried to make a practical approximation algorithm. So they work they don't really focus on develop an algorithm with a good analytical convergence. But in our case, our main motivation was to develop an algorithm with good analytical convergence. So I think that was the difference. So they didn't really focus on that direction, I think. It's more like practical approximation algorithm.
So just to clarify something for myself, maybe you've already mentioned this, but when you're thinking of good analytical convergence, you're thinking of convergence in terms of the number of
answers and questions,
and not in terms of the dimension of the state.
Yes, because as our assumption is we fix the dimension t, right? So t is always number in our case.
Yeah.
So I think the relevant terms are more like A1, A and Q, because they are the variables you can change. So t is just number in this case.
Yeah, gotcha. Thanks. All right. So in the Slack we have lots of claps, which means that your talk is very clear to everybody.
Okay. Thank you.
So thanks a lot, Hailey, and thanks for giving the final talk of the QuAlg workshop. So a couple of announcements before we head out. So there will be some announcements announcing this student prize in maybe 15 to half an hour in the announcement channel on the Slack. So please stay tuned for that. And I really shouldn't go before thanking the people that were behind running all of this workshop, QuAlg, and the whole quantum eco fun. We're working very hard behind the scenes to make everything run smoothly. So a big shout out to Katie Isham, Destiny Chan, and also Oliver Dent and Zain Hussein, who are in charge of the tech part of all of these talks. And I guess finally,